So chapter 9, we're going to start. Chapter 9 is about the molecular geometry, and we're going to also explore some more bonding theories. So the one that we have talked about is Lewis theory, and we are now going to talk about VSEPR, which is related to the geometry of the molecules, and then we will expand on that and go on to valence bond theory, which is your hybridization, like your sp3, whatnot. And then after that, we may or may not talk about molecular orbital theory based on how much time we have, okay? So the first part of this chapter is just going to be on VSEPR. So it should be a quick review for you guys on what VSEPR is. All right, so VSEPR stands for valence shell electron pair repulsion theory. It's in the name itself. So VSEPR is based on the repulsions that atoms of a molecule will feel based on the electrons that are in their valence shells, because those are the shells that are involved in bonding, right? Core shells are not involved in bonding. It's going to be the valence ones that are involved in bonding. Now, with electron groups, every electron group that is here in this list is going to be counted as one electron group, okay? So if you have a lone pair, that is considered to be one electron group. Everything has the same weight. A single bond has the same weight as a double bond and a triple bond, okay? So when you're counting your group, you count lone pairs as one, single bond is one, double bond is one, and triple bond is one, okay? So 4 electron groups are present, and they have repulsion. And there is a hierarchy of repulsion. Lone pairs repel the most, okay? Lone pairs and bonding groups next, and then the next lowest repulsion is between bonding groups and bonding groups. That means like bonds will repel each other less than lone pairs and bonds, but lone pairs and lone pairs will have the most repulsions inside the molecule itself, okay? The preferred geometry is going to be where you have the electron groups with the maximum possible separation from each other to reduce the repulsion. And when that separation exists, the molecule is stable and the potential energy in that molecule is low. So you have a minimum energy state, okay? Then we are going to go through different types of VSEPR, but we are mostly going to be dealing with molecules with one central atom, and then we will apply it to molecules with multiple central atoms, okay? So in molecules with one central atom, the molecular geometry, the geometry of the actual molecule, depends on the number of electron groups. So remember, each electron group, lone pair, single, double, triple, has a weight of 1. Those electron groups are around the central atom, okay? And it also depends on how many of those electron groups are going to be bonding versus lone pair. So here are the basic shapes. You should know these shapes already, but we're going to look at them in greater detail. The molecular geometry is basically based on how do those repulsions around the central atom affect the overall shape of the molecule, okay? So we'll deal with the first VSEPR shape, which is going to be a linear shape. So the first situation is where you have 2 electron groups, both of them are bonding, and you have no lone pairs, okay? Here is an example, BeCl2. Now you might remember when we were learning about Lewis theory, I said that one of those things that is happy with not having an octet was beryllium, boron, and aluminum. So this is a situation. Beryllium really only wants 4 electrons around it, okay? So it has these 2 single bonds bonded with chlorine. And if you have 2 bonding groups and no lone pairs, you have a linear electron geometry, and you also have a linear molecular geometry. So I know last year in honors, you may have mixed electron and molecular geometry up, but we are going to separate them, okay? We are going to separate them and look at them individually. So for every molecule we'll examine, you'll have electron geometry, but also molecular geometry. So in this case, electron and molecular are the same, but it's not always the same, okay? The bond angle, obviously, for a linear molecule is going to be 180 degrees. The bond angle is counted as between 3 atoms with one central one. So chlorine, beryllium, chlorine bond angle is 180 degrees, okay? like so. Okay, and you can see the 3D model here moving. You can see that it's just a linear molecule. All right, now here is the second one that we're going to look at. This one has 3 electron groups and all of them are bonding. You have no lone pairs. Here is an example, BF3. Again, remember boron is happy without an octet. So boron has 6 electrons around its single bonds bonded to 3 fluorines. And because it's a triangle, the interior angle of that triangle is going to be 120 degrees because all around this central point is going to be 360 degrees, right? So the electron geometry is trigonal planar, the molecular geometry is also trigonal planar, and the bond angle is 120 degrees. This is called trigonal planar because it is on the plane. It is a planar molecule. If I take, this is the plane, right? If I take, like, let's say this is a piece of paper, I could slice this molecule through its central atom and every other atom in half this way. Okay, so now look at this particular molecule. This is also a trigonal planar molecule. Okay, um, but you'll see that the bond angles are slightly skewed, and the reason is because of this double bond. So the repulsion from this double bond, remember, the repulsion increases the more electron dense a bond is. So if all 3 bonds are single bonds, they repel each other the same and they will arrange each other equidistant from each other with the same bond angles. But a double bond has more electron density, which means that the double bond will push the carbon-hydrogen bonds down, causing the bond angle between hydrogen-carbon-hydrogen to be lower than 120, so 116.2, and then it will push the, because these bonds have been pushed down, this bond angle right here is larger than 120, that becomes 121.9, which is larger than the ideal trigonal planar bond angle, okay? But it's still 3 electron groups, all bonding, no lone pairs, so it still counts as a trigonal planar molecule, okay? All right, so the next shape is going to be where you have 3 electron groups, just like before, but 2 of them are bonding groups and 1 of the electron groups is now a lone pair. So here is an example, sulfur dioxide, and in this particular case, the electron geometry is still trigonal planar because of the fact that it has 3 electron groups, but the molecular geometry is now bent. So it's called bent because this lone pair is repelling these double bonds down, okay? And because of that, you have this bent geometry and the bond angle is going to be less than 120. Now you might be wondering, why don't we do specific bond angles instead of doing something less than the ideal? It's because every single molecule that you're going to encounter is going to have its own bond angle that is very specific, and it is impossible to remember all of those. So because of that, we say it's less than 120 if it is this geometry, okay? So this is 3 electron groups, 2 bonding, 1 lone pair, electron geometry trigonal planar, molecular geometry bent, and the bond angle is less than 120. Then the next one that we're going to discuss is where we have 4 electron groups, and all 4 are bonding groups and none of them are lone pairs. So when you have this kind of geometry, we say that the electron geometry is tetrahedral and the molecular geometry is also tetrahedral. They're the same, and the bond angles are 109.5, okay? So the bond angles are 109.5. It is the interior angle of a tetrahedron that is the 109.5. There is a proof, little throwback to your geometry days. I don't know anyone that actually super enjoyed geometry, but if you want to go back to your proof days, there is a proof that tells you why the interior bond angles of a tetrahedron is 109.5. Okay, little throwback to freshman honors geometry. Okay, so this is what a tetrahedron looks like. Each atom forms one point of a triangle. You have 4 triangles, 1 on the bottom, 3 on the sides, and then this bond angle is going to be 109.5. Okay, now the next one is going to be 4 electron groups, but 3 of them are bonding and you have 1 lone pair. Very common molecule, right? You're familiar with this. This is ammonia. So electron geometry is still tetrahedral. Molecular geometry, however, is now trigonal pyramidal, meaning it is a triangular base pyramid. And one of the points of your tetrahedron still for the electron geometry is made up of the lone pair, but because lone pairs don't necessarily have a particular location as a point, it can't be a tetrahedron anymore. And this repulsion from this lone pair up here is going to reduce the bond angles to less than 109.5. So we remember it as less than 109.5, but you can tell the specific angle of ammonia is given here. It is exactly 106.7 between hydrogen, nitrogen, and hydrogen. Okay. Ideal tetrahedral geometry will have a bond angle of 109.5. The next one is going to be still 4 electron groups, but now we replace 2 of the bonds with 2 lone pairs. So you have 2 bonding pairs and 2 lone pairs. And again, the electron geometry is tetrahedral. Molecular geometry is now bent. This is also called bent geometry. Water is a very common example used to show bent molecular geometry. And the bond angle is again less than 109.5. And you'll see that the bond angle here is actually 104.5 between hydrogen, oxygen, and hydrogen. And 2 corners of the tetrahedron would be 2 lone pairs. 2 bonds have been replaced by 2 lone pairs, but the electron geometry is still tetrahedral, okay? Because it's just based on electron groups by themselves, but molecular geometry actually takes into account the repulsion that exists between these, okay? So you have this and this, like little Mickey Mouse ears on oxygen. Okay, so all right, sorry kids. So the next one, one of the questions over here on water that people ask me is why can't we draw this linear like this? Just drawing with my mouse pad, so it's not the best drawing, but whatever. Those are the lone pairs, okay? Why can't we do 1 lone pair on top and 1 lone pair on the bottom? It's because this particular arrangement of lone pairs and bonds is not the maximum possible arrangement that gives you the lowest possible energy. You might think, oh, that's the furthest, but it's actually not, okay? In order to get the maximum possible distance from each other, lone pairs and bonding groups, they do automatically arrange in this tetrahedral geometry for electron geometry and this bent way where the lone pairs have the maximum possible distance from each other, which is why this particular bond angle is squashed together to be 104.5. Okay, so the next one is 5 electron groups. All of them are bonding groups and none of them are lone pairs. We call this electron geometry trigonal bipyramidal because the center plane, you'll see if you connect this atom, and that atom, they form a triangle. And then these top and bottom are the points of that triangle. So like this, and then these will all connect to that. You'll form that trigonal pyramidal. Oops, you can see what I'm drawing. But yeah, trigonal bipyramidal geometry. Okay, so 2 triangles bipyramidal with a triangular base. Electron geometry and molecular geometry are the same because all of them are bonding and none of them are lone pairs. But this one has 2 bond angles. So we have equatorial bond angles. So just like the equator on our planet, if you cut this molecule in half on the equator of this molecule, because it's a triangle and the interior angles of a triangle are 120 degrees, and around this phosphorus in this example, PCl5, the ClP-Cl bond on the inside is going to be 120 degrees, okay? Because you're dividing 360 by 3. Then the equatorial bond angles, sorry, not the equatorial, the axial bond angles, because this is part of the axis. If you draw a straight line through it, that's an axis. the axial bond angle is 90 degrees. If you add both of them, it's 180, but each axial bond angle, chlorine, phosphorus, chlorine, is going to be 90 degrees, okay? So that is 5 electron groups. Now, let's do 5 electron groups with one lone pair. So 4 bonds, 1 lone pair. The electron geometry stays the same. It's trigonal bipyramidal, but the molecular geometry is a seesaw geometry. Okay, so seesaw, it looks like a seesaw, like you could put, it's like a sideways seesaw. You could have someone sitting here. Okay, and someone on this side too. That's why it's called a seesaw. It's not the perfect one. It's kind of a skewed seesaw, but the lone pair here basically pushes all of these bonds together, squishing them, and the equatorial and axial bond angles change. The equatorial bond angle here is much smaller, and then the axial bond angle is going to be less than 90, because if you divide 173 by 2, you're not going to get a 90-degree bond angle. Okay, so seesaw geometry, the lone pair is right there. Okay, next is going to be 5 electron groups, but 3 of them are bonding and 2 of them are lone pairs. Still trigonal bipyramidal electron geometry, but we call this one T-shaped, the molecular geometry, because the repulsion from these two lone pairs is going to squash those bonds together to form kind of a T. It's kind of a skewed T, and the bond angles are going to be less than 90. If it was a perfect T, these would be 90 degrees, right? But it's not a perfect T, so you have less than 90-degree bond angles, okay? Then you still are in 5 electron groups, and now you have 2 bonding and you have 3 lone pairs. So every one of the trigonal bipyramidal's triangular base has been turned into a lone pair. So I think that was the wind. Sorry about that loud bang. But okay, so these 3 lone pairs on the central xenon, just the sizes are indicating that this one is just going away from the plane, this one is up, and this one is down, but they are both in the plane. Okay, so this is what it would look like, the 3 lone pairs, and because all 3 of them are lone pairs and they are repelling each other and locating themselves at equidistance locations, you have a perfect line here with a linear bond angle of 180 degrees between those 3 atoms. Okay, so so the next one is 6 electron groups, all of them bonding, no lone pairs. You can see SF6 here. The electron geometry is octahedral, so is the molecular geometry. And the reason that it is octahedral is because if you connect all of the atoms with lines, you get an octahedron with a square base here, if you look at it as a square pyramid, and then you have 4 triangles on the top and 4 triangles on the bottom with a square pyramid in the middle. Okay, so it has 8 planes here, and it's an octahedron. Okay, and all of the bond angles are 90 degrees, so that's going to be 90-degree bond angle. All of them are 90-degree bond angles. Okay, then you have 6 electron groups here with 5 bonding groups and 1 lone pair. And the electron geometry is called octahedral, and the molecular geometry is called square pyramidal. It's because if you connect these corners, wow, that's terrible. If you connect these corners and you connect each of the corners to the top, you get a square pyramid. Okay, so the reason that the bond angles are less than 90 degrees is because this lone pair squashes those bonds forward, so you lose that 90-degree perfect bond angle, but it's still considered to be square pyramidal, even though those bond angles are not 90 degrees. Okay, you can see here you have BRF5. The lone pair is pushing the bond angles, and it is less than 90, 84.8 to be exact. The picometers are basically the bond lengths, and you'll notice that some of these lines here are like thicker, and then these are the dash lines. This is called wedge notation because literally they're using wedges. The thick wedges that are drawn like this is just showing things that are coming out of the plane. So if I put a piece of paper down this way, this line here is in the plane with the paper. These two lines are coming out of the paper, like coming out at you, and the dashed lines are going in away from the paper. Okay, that's what that basically means. All right, so this might be the last one. The next one is 6 electron groups. You have 4 bonding groups out of the 6 and 2 lone pairs. So if you make the central atoms, atom have the lone pairs over here, right? That's how the Lewis structure will work out. If the top and the bottom are lone pairs, then the molecule will orient itself so that you have a square right here, and the electron geometry in this case is still octahedral. Remember, that's just based on the total number of electron groups, but the molecular geometry is now square planar. So it's a square that's in the plane. I could take a piece of paper and slice through all of these atoms horizontally, and I'd have two equal sections on either side of that paper. Okay, the other planar molecule that we saw was trigonal planar. So this is square planar. You have one more atom here. Okay, that forms that square, and the bond angles obviously are going to be this way, 90-degree bond angles. Okay, so you have 90-degree bond angles inside the square planar molecular geometry molecule. Now this is XCF4. This thing you should ignore. We don't have sp3d2 hybridization. I don't think you learned it in honors, and I used to teach dehybridization because it seems to explain this particular molecular geometry really well. But we are not going to do that hybridization because currently it is under review, and AP has drawn a line saying don't teach it because of the fact that we're not certain that that is what happens yet. Okay, so bonding theories are constantly in flux, so it is quite normal to have this kind of thing happen. Okay, so that was the last of the geometry, so you are welcome to stop the video now. That was the lecture part of it, but the rest, I think I'm going to do a couple more slides just explaining a few questions. Okay, so here is nitrate. You have drawn this structure as a Lewis structure, I'm sure, last year or this year. This is the structure of nitrate. You'll notice this is obviously an anion with a -1 charge. Nitrates, oxygen, the top oxygen is holding the double bond here, the left oxygen is holding the double bond here, and the right oxygen is holding the double bond here. These are equivalent structures because you can easily rotate these molecules so that the double bond goes from here to there and then from there to there, etc. But you know that from what we learned last unit or chapter, that nitrate doesn't actually exist as one of these. It exists as a hybrid of all three of them, and we have evidence of that. It's because when we try to measure the bond lengths of these bonds, we expected the double bond to be shorter and to have two single bonds, but we got was 3 equal length bonds, which indicates that all of the bonds have partial double bond character, and that it's a hybrid of all 3 of these that we have as the actual nitrate anion. Okay, and the molecular geometry agrees with that because the bond angles in the nitrate anion are 120 degrees, which indicates trigonal planar geometry with equal repulsion between all 3 partially double bond-like bonds. Okay, here's a question. Which statement is always true according to VSEPR theory? So let's look at all 4 answers. A says the shape of the molecule is determined only by repulsions among bonding electron groups. That's not true. The shape of a molecule is determined only by repulsions among non-bonding electron groups. That's not true either. The shape of the molecule is determined by the polarity of its bonds. No way. Polarity has nothing to do with it. Okay. The shape of a molecule is determined by repulsions among all electron groups on the central atom. That is the correct answer. So D is the correct answer. Okay. We will do this one in class. All right.